Hi everyone. So my name is Pablo. I work at Elastic. I have a very strong background in distributed systems, Hadoop, and also Elastic and Elasticsearch. I'll be talking about a bit on the Elastic Stack. Not so sure how many of you are familiar with the entire stack. Then I'll go into monitoring architectures. So as you want to monitor your logs or metrics, your systems, what are the common architectures we have? Then I'll go into some cluster sizing, not specifically a shard sizing. There's a talk about that, but the overall idea and how to think about scaling when it comes to logs. Then 2 tips on optimal bulk size, so when you're ingesting, how to do that, and distributing the load is also a very important part. So let's get started. First of all, the Elastic Stack. So who here knows Beats? Few. Who is using Beats? Okay, nice. Logstash? Knows Logstash? Heard about Logstash? It's using Logstash? Okay, Elasticsearch? Yeah, now it comes. All right, log. And finally, Kibana? Okay, good. 50%. So let's start with Beats. What's Beats? So the idea of the entire stack is to be able to ingest data, store data, and analyze data. So when you want to ingest data, you might have a server or an application that's running whatever you have. And when you want to get logs out of there, or even metrics like CPU and RAM information, you don't want to put a lot of load on top of that server, because the main goal of that server is to serve your application, is to serve your users. So the idea of Beats is you have a data shipper, you have a lightweight agent that's just collecting information and send it as lightweight and as fast as possible somewhere else. So it's what we call the application side component, a small agent that will be installed, and it's going to be collecting those metrics. You can collect those metrics from logs. You can collect those metrics from wire, like PacketBeat that connects network traffic. You can just collect metrics, CPU, RAM information, or metrics from any Nginx process or an Apache process that's running. So as you get this information, sometimes as you get log files, you need to parse it. You need to do some processing on that. And that's what Logstash is for. And you can have one node for Logstash or multiple nodes. And the idea is that Logstash can still do data shipping, can still collect data with inputs and also write to outputs. But the main goal is to do data enrichment. It's to be able to parse this data. So Logstash is not as lightweight as Beats is, but it gives you much more flexibility and also much more power to actually parse and enrich your information. And then, as you want to store your data, you put this data in Elasticsearch. And I'll talk more about Elasticsearch later, but the idea is that you have a data platform. You can store your data, you can do full text search in your data, you can do analytics in your data. So a lot of different things regarding exploring your data. It's really, really fast. So you get responses in milliseconds. Of course, it depends on the size of your data and your architecture, and I'm going to give some good tips for that. And it's very easy to communicate to. So just sending HTTP requests and JSON bodies, you can use Elasticsearch APIs to do everything Elasticsearch can offer. So we got data from your application machine, we did some processing, and we are storing this data. But the data is stored as text, as strings. So how can we actually visualize this data? And that's what Kibana is for. Kibana is the UI part of the stack that allows you to get this JSON and transform that into nice visualizations, into nice charts. All right? So this is the stack. And besides the open source, so you can download and use any of those components. They are totally free. We also have the customer part, which is XPack, which I'm not going to talk about, just for you to know. So we add some extra functionalities. And we also have a hosted service, which is called Elastic Cloud. I heard a few questions before about, okay, but there is Elasticsearch in AWS. Do you have anything with Amazon? No, we don't have. They have their own service. We have ours. Feel free to check. So let's go into the interesting part, monitoring architectures. So we got Beats collecting data, and you can send data directly to Elasticsearch and visualize this data. Then, if you want to do some extra processing, you have Logstash, as I said. So, for example, if you have an IP information, there is a filter that allows you to do GeoIP enhancement. Based on the IP, it gets the latitude and the longitude, so you can look into requests coming in a tile map. Logstash is very flexible. We can also get data from multiple inputs. So you can get data from Twitter. You can get data from sensors. You can get data from any HTTP that you can request and get information out of it. So the idea of Logstash is being very flexible in terms of getting data, but also in terms of writing data, of outputting data. So you can write to Elasticsearch, but you can also write to queues. Kafka, for example, it's a very interesting place to put your information. Storages like S3. Sometimes you want to put your data in Elasticsearch, so you want to do full text search and analysis. But you just want to look into this data for the last 7 days. But you cannot throw this data away in terms of auditing. So you can write to Elasticsearch and at the same time write to S3. So the data is there. And then you analyze the data in Elasticsearch, but you really persist the data in S3. Metrics, notification, PagerDuty, Slack. And to finalize the journey event, you have here a messaging queue. So as you are streaming information and going to Logstash and Elasticsearch, sometimes the processing is not fast enough. So you might lose some data that's coming, especially with metrics. If you're reading from files, log files, that's usually not a problem because Beats can just stop reading from the file or even Logstash itself. But if you are collecting metrics, there is no place to write them. So in many cases, you send that to the messaging queue, and then it's persisted, and then you can finally do the reading, the processing, and go into Elasticsearch. So this can go really, really complex. You can see that we have even different nodes of Elasticsearch that can do different processing. So that was the Elasticsearch architecture aspect. So let's try to go into, okay, but how do I size all of that? How many nodes of Elasticsearch? How does Elasticsearch works internally? So for those of you that are not familiar with Elasticsearch, we have a common terminology. So there is a cluster. This is where everything lives in Elasticsearch. You have a server. This is just a machine like my laptop that is running Elasticsearch. And when you start an instance of Elasticsearch, we call that a node. And as you write data into Elasticsearch, we say you are indexing a document, that's what data is for us, into an index. And an index is just this logical grouping of documents. Just like a table in a database, that's what an index will be in Elasticsearch. But the real working unit that we have is shards. Because Elasticsearch is a distributed system, we need a way to distribute data. And instead of doing what I like to call the late data splitting, so after you have a lot of data, you decide to break things and spread them in the cluster, we do the early data splitting. So beforehand, when you create your index, you need to tell Elasticsearch how many partitions, how many pieces would you like to have. So later on, it's easier for you to just distribute this information. This is what we call a shard. This is the working unit. And for those of you that know Lucene, each shard is going to be a Lucene instance. We name shards from 0, adding up 1 on every shard you have for an index. So this would be shard 0 of the Twitter index, shard 0 of the logs index. Okay, it was built for scale, so you can add a second node of Elasticsearch, and this will be added to the cluster, and automatically Elasticsearch will distribute the load. What does it mean? Getting a few shards and copying them over to another node. As we get more nodes and we start scaling, there is another problem. What happens if a node fails? And then you lose data. So we have the concept of replicas. So by default, every index has a 1 replica per shard. So in this case, we had 5 shards, and now we have 5 replicas. And we call them primary shards and replica shards. And now, if for any reason node B fails, we have all the data in node A, and they can just take over. And if we had another node, like node C, Elasticsearch again would just automatically distribute the data. So Elasticsearch is taking care of putting the data across the nodes you have, and making sure that when you search, we go into where we need to go to get this information. Okay, so how do we scale? So when I think about scaling, I think about data. We have data, and we need to put data somewhere. And when your data is small, you can put your data in one machine. And as your data grows, you then need another machine, so you need more processing power, you need more RAM, you need more disk. And as your data grows again, you need more machines. And finally, you keep on adding machines. So for the size of your data, you need to think about, okay, how many machines or how many working units do I need to solve the problem I have? If you think about Google, and you just think about one user executing one search, if you want one search really, really fast, with the amount of data that Google has, how many machines, how many working units do they need to serve one single request? Okay? So that's the first layer of the map reduce. That's the first layer of the divide and conquer. So in Elasticsearch, those working units are called the shards, as I just explained. And the more data you have, the more shards you need to distribute the loads and guarantee that things are fast. But how many shards? And that's a very common question that I get in trainings, and it's also a hard question to answer because it depends. First of all, how much data do you have? So let's just think about 1,000 events per second, 60 seconds, 60 minutes, 24 hours, times 1,000 events. That means 87 million events per day. Each event will be 1 kilobyte, so something around 82 gigabytes per day. That's an ingestion. That's not a lot of data. But I want to keep this data for 3 months, which means that at the end of the day, we are going to have something around 7 terabytes of data. But what is the ideal shard size? If the shard is the working unit, and I know how much data I have, I need to know how much data can I put in one working unit. And that's not exactly what I'm going to talk about. You can find that information in a very good talk where we actually go into detail of the shard size. But I'm going to say, okay, I know the shard size. It's 45 gigabytes. That's the ideal shard size that I did after calculating, looking to this talk. And I know that I could have 10 shards per machine. So with that calculation, how many nodes do I need? What is the sizing that we need to do? So the data size is 7 terabytes. The shard size is 45 gigabytes. That means I would have something around 160 shards in my cluster. But I should have 10 shards per machine. So how many machines should I have? A total of 16 servers. And again, this is for 3 months of log. This is the first part of the problem. This is how many nodes do we need to have to basically serve one single request as fast as we need. Okay? But how many indices? If the index is the logical grouping of documents and each index is going to be broken into shards, and you just said that we should have something like 160 shards, how many indices should I have? One single index with 160 shards could be a possibility, but maybe not a good idea. What do you do if the daily data grows? So we are assuming we have 82 gigabytes per day, but when Black Friday comes, from 82 you probably go into 160 or 240. So it's very hard to predict the data for tomorrow. And especially if we have 3 months of data, this will change. The requirements change over time. You cannot have the same requirements forever. How do we delete old data? Deleting old documents is going to be too expensive. There must be a better way of just deleting documents. We might want to group documents per day or per week and delete all of them together, which will give you a better performance. So that brings the topic time-based data. And time-based data is very common nowadays. We are talking about logs, we are talking about social media, sensors, getting this information. It's basically a timestamp, so when the information was collected, associated with the real data that we want, like the CPU measurement or the Apache logline. Does not change. It's rare for you to go back and change time-based data. you want to search for recent events, the last 7 days, the last 30 days, the last 1 year. Each company will have different requirements, but usually you are interested in the same period of time again and again and again. Older documents become less important. It's hard to predict size, as I said. So for time-based indices, for time-based data, time-based indices is going to be the best option. What does it mean, time-based indices? It means you should create indices in Elasticsearch based on time. Depending on the data you have, hourly indices might be a good idea. You need to have a lot of data, but we have users doing hourly indices. In general, Logstash and Beats, by default, they create daily indices. Sometimes it's better, instead of daily indices, for you to have weekly indices or even monthly index. It depends on your data. And yes, when you search, it doesn't matter if you have your data spread across different indices. Elasticsearch allows you to, in the same request, in the same search, go into all those indices at the same time. So it doesn't matter how you separate your data. When you do search, that's going to be transparent. We are going to get all this data and give you exactly what you're looking for. So let's take a look into an example of daily indices. So we have logs and metrics going on, and I decided to do daily indices. So in 2006, then 19, I create an index, and then we ingest this data into this index. And then the next day, I create a different index. So now I have the index from yesterday and the index from today, and I keep indexing the data to the new index. So tomorrow, we then create a new index so we can write data to this index, but when we read from all of them. You're probably looking into this and thinking, okay, but how do we manage that? It looks like too complex for managing those things. And we have a few nice features that can help you with it. So the first one is templates. As we create a new index every day, you don't need to be awake at midnight to basically create the mapping. The mapping is the schema in Elasticsearch. To create the mappings and the settings for your new index. You can define templates in Elasticsearch, and those templates will be applied every time a new index is created that matches this. So every new index that starts with logs dash, it's going to use those settings that I'm defining here. And you can change that. If your data grows and you know that starting tomorrow you need more shards, you can just come and update the template. So every time a new index is created, it's going to be created with 2 shards and 1 replica instead of 5 shards and 1 replica, which is the default. And there is also the refresh interval that I'm going to talk about later. So more than that, a common thing is to use alias as well. This is another feature that's very interesting in Elasticsearch. It allows you to coordinate reads and writes without having to bother your application or your end user. So here I have users reading data from Elasticsearch. And instead of pointing your application directly to the indices, we create this idea of a symbolic link, which we call alias, that's actually pointing to the indices you want. So the first day that you create the index, you are writing to this index and reading from this index. But then the next day, you can change the logs write. This is the alias pointing to the new index we want to write. And the logs read is going to be pointing to both. And then on the third day, you can do the same thing. And more than that, you can add the alias to the template. So as you create a new index, it will automatically apply the alias to that index. And even more, there is a feature, I don't have time to talk about it, it's called the rollover. It's an API that you can call that helps you doing exactly this rollover, either based on time, 1 day, 2 days, or based on size. And the size is the number of documents. So you can say, okay, I want a maximum of 1 million documents. And then as you call the API, it will roll over automatically to the next index. Good. If you need to go out of here and remember one thing is do not overshard. Why? Because it's not going to perform well, and it's very likely to happen because the defaults for Elasticsearch are really nice for you to get started. The out-of-the-box experience is what matters to us. However, it's not very good for production. 3 different logs, access logs, application logs, and MySQL log. 1 index per day each. That's the default in Logstash and Beats. 1 gigabyte is going to be each of those indices. 5 shards, that's the default we have. 6 months retention, that's your requirement. So this means 180 gigabytes in 900 shards. That's not good. Not good at all. This is too many shards. When we do search, we need to get information from all the 900 shards and then coordinating that, merge that result to give the user one single final result. Especially 180 gigabytes of data, that's not a lot of data. You can easily put in a shard 30 gigabytes, 45 gigabytes. So I would easily solve this problem with 10 shards. Why do we have 900? Oh, because that's the default in Elasticsearch. You just got started, it's very easy. Yes, but please do not overshard. This is like #1 cause of support issues we have. Okay? So this was the reading, scaling with the amount of data you have. But now we need to think about users. If that answers 1 million users, how can we answer 2 million users? That's replicating. So you create replicas of the data. This will serve 1 million, this will serve 2 millions. And now if you had 3 million users, you increase that. What happens in Black Friday? You used to have, I don't know, 1,000 requests or 1 million requests an hour, and now you have 2 million, or even 10 million because people go into your website more and more and more. And then you have more logs and more data coming in. So what do you need to do? Start more machines and increase the number of replicas. And the number of replicas is a dynamic setting in Elasticsearch that you can increase and decrease as you want. But make sure you provision the nodes so you can actually do this scalability in the right way. So big data access, user access, that's how you think about scaling Elasticsearch. All right, so shards are the working unit, primaries, more data, more shards, write throughput, more writes you need more shards as well. Replicas, they'll give you high availability. If something fails, you still have the data and also give you read throughput. The more reads you want, the more replicas you need to provide. All right, so now, not a lot of time. I'll try to go into 2 tips for optimizing things when you're writing to Elasticsearch, especially for the logs use case. Let's try to do that in 5 minutes. So the first one is optimal bulk size. But wait, what is bulk? Bulk is how we call the API for you. Instead of sending 1 document in a write request, you can send 1,000 documents in 1 single request. It saves you bandwidth, it saves you a lot of different requests you are opening, file descriptors, etc. So bulk is the way to go if you want to write many documents at the same time. So for the logging use case, make sure you use bulk from your application. Beats and Logstash do that by default. But what is the optimal bulk size? I don't know. Why? It depends. It always depends. But on what? It depends on your application. It depends on the number of nodes you have. It depends on the number of shards you have, on the sizing you did, on the bandwidth, on a lot of things. Okay, but how do I calculate that? Don't calculate. Just test it. 4 times 250, 2 times 500, 1 time 1,000 documents. So let's go. Put your setup, and then try to index everything. So here I'm getting 1 million events, and I'm trying different setups. And then I'm measuring the time to decide which one is the best one. Is it 250, is it 500, or is it 1,000? It's not too hard to write a script. It's actually a very small one. Basically what I'm doing here is doing a loop with the different values, all right? Executing the test 20 times, because this is a distributed system. A lot of things will influence on that, especially the round robin that I'm going to talk in a bit. So you want to have a lot of different tests. So test 20 times, calculate the average, discard the outliers before, and you should be fine. And this is a Logstash setup. I'm reading from the standard in, so I'm doing a cat here with a file with 1 million lines, and then the flush size is going to be one of those parameters. So that's the size of the bulk we are sending. Collect the result with time, and that's it. So the results we got here, so 100, you get 191. You can see that 100 is a bad idea, but from 500 to 10,000 it's almost the same. It doesn't matter too much in this use case. It's a simple use case. I was just testing to show some numbers. Do in your production environment. And then distribute the load. So when you send a request, your request goes into a node. But if you send always the request into the same node, this is going to overload the node. This is the bottleneck. So it's good to distribute the load. We have 3 ways of distributing the load. So the client, your application, most of them already implement that. So if you get the Python client for Elasticsearch, it will already implement round robin. It will connect to the cluster, get information about all the nodes, and automatically do the round robin. Logstash and Beats allow you to provide an array, and they will round robin between the nodes in the array. They will be not smart to sniff the cluster, but they will round robin. And Kibana only connects to one single node. So Kibana needs a different way of scaling. Another option is a load balancer. Trivial, just put a load balancer in front of the cluster, and the load balancer will distribute the load. And the third option is what we call the coordinating only node. It's a node that does not contain data, does not do anything. It serves as a load balancer plus the reduce phase. When we do search, remember I said we need to merge the information from all the shards we have. This can also be executed in the coordinating node. So it's somehow a smart load balancer, and it's another way of distributing the load. So I redid the test. Now, before I had 2 nodes, and I was just sending the request to one. And now I'm round robin the request between the 2 nodes we have. And you can see it's not a big improvement, but yeah, that was an improvement. And this was a simple test. If you're actually in a high load, this goes even more, especially if you have more nodes. This case was just 2 nodes. If you have 10 nodes and you always go to just one, that's not the right way to scale. Okay, so yeah, that was it. Final remarks. So this is the journey of an event. There's all the ways you can ingest, process, and store data. Primaries, more data, more shards. Please do not overshard. Use replicas to do high availability and also increase read throughput. Remember, big data access, user access. This is replication. This is the number of shards you need. And yeah, bulk, use it and test, and also distribute your load. Okay, thank you very much for coming. And if you have any questions.
Thanks, Pablo. Are there any questions for Pablo? Yes, I see one hand.
Thank you. If you have an 10 shards on an instance, what kind of instance type do you have?
Sorry, if you have 10 shards?
10 shards on an instance.
Okay.
What kind of instance type do you have?
Ah,
if you
all
compare
right.
it to an Amazon.
We usually don't go into very large instances. So instances with more than 128 gigabytes of RAM, that's usually becoming too much. We usually prefer instances with 64 gigabytes. It's a lot about the ratio between the memory and the shard size and the storage that you need. So in that case, I have 45 gigabytes. So that's a lot of data in a shard. Usually a shard goes between 20 and 50. So that was kind of the limit, just to prove my point. So in that case, you probably would need a more robust machine. I would say something like, yeah, I don't know. I don't remember the AWS correctly, but something like 6, 8 CPUs, 96 gigabytes of RAM should be fine. But again, it depends on your requirements, right? Here I didn't say, but when you do the shard sizing for the capacity planning, what you get back is basically that size shard is based on your requirements. So if you want responses from a search request to be below 100 milliseconds, then you probably want a shard size of 30 gigabytes. And then if your requirements say that, okay, you can go actually to 200 milliseconds of a response time, that's fine to your application. And then you can actually put more data in the shard size. Especially when we are talking about log use case, you don't care too much about the response time in terms of searches. You're just rendering dashboards every 5-10 seconds just to see how things are going. So you can actually increase that a lot, but the index throughput is what matters. So you actually want to use that as the baseline to make sure, okay, this is meeting your requirements.
Hey, so in the diagram you had in the beginning with the replications of shards, just quick question for you there. You were saying, you know, they get stored across. If you have failure in one node, you get, you know, obviously the backup. Does that by default keep one replication per shard and store it sort of on some random other machine, or is there some way to configure that and some sense to that?
Okay, so by default, what we have is 5 shards and 1 replica. That's how we call it. And I like to think about the number of replicas as the replication factor. So by default, it's 5 primary shards and 5 replica shards. Okay? And this will be distributed across the nodes automatically. You can increase that, you can decrease that. There are a few settings. They are called, one is shard filtering, and the other 2 are shard awareness and forced awareness. So the shard filtering, you can use the hot and warm architecture and say, all the shards from the index from today, I want them in the hot machines because those are the ones I really want to be really fast because I need to write. And then all the other shards from the different indices, this is a per index setting. I want to move those into the warm machines. This is shard filtering. The other one, which is awareness, you say, okay, I have racks or availability zones in the AWS. So I want Elasticsearch to be aware of that and don't put replicas in the same availability zone as primaries. So I want Elasticsearch to be aware of that and move. And the forced awareness is, I don't care about failure. I never want replication in the same availability zone as my primaries. This is a common setup when you don't have enough resources. So actually, if we started replicating here, we would just basically queue the nodes. And then you say, OK, I want to force the awareness and do not over-allocate on this availability zone, rack, or server if you have virtualized environment.
Cool, thank you.
Any more questions? No? Okay. Thanks,
Thank
Pablo.
you.